Okay, guys, welcome to today's lesson in statics. Today we're covering problem 24 from chapter 3. So number 24 says, the wooden board AB, which is used as a temporary prop to support a small roof, exerts at point A on the roof a 57-pound force directed along BA. Determine the moment about C of that force. So first, I would start off by drawing a Freeburg diagram. We have our point C, we have our point A, and we have B down on the ground. Now we know there's a force directed along the board in the direction from B to A, which is force BA. We know the magnitude of that is given to us as 57 pounds. So write the scalar value FBA equals 57 pounds of force, a little reminder. Now looking on the diagram, we have point C on the top of the roof, point A on the bottom of the roof. We're going to have to find the vector going from C to A. So illustrate that in red right now. So we need this vector going from C to A in order to determine the moment. First, let's go ahead and just write out the moment equation. The moment about C is equal to the position vector going from C to A. So R, C to A, cross our force at point A, F vector BA. Okay. Now we know we can figure out this vector looking at the diagram. So looking at this red arrow representing point C to point A, in the x direction we're going to on the positive x-axis 48 inches. So we write out our vector RCA, that would be equal to positive 48 on the x-axis, or 48 I hat, positive 48 I hat. Looking at vector C to A in the y-axis, it looks like we appear to be going down about 6 inches right here based on this dimension. So minus 6 j hat. Good. And finally, looking at the k vector in the z-axis, we appear to be going out 36 inches out of the page. So we would have plus 36 k hat. Now to determine the force vector BA, we need to first determine the position of it, position vector going from B to A. So we find position vector R, B to A. So position vector R, B to A, would start at point B and go to point A. So start on the ground, we appear to be going in the negative x-axis direction, negative 5 inches. So we have minus 5 inches in the I hat direction. On the y, going vertically, we appear to be going up the wall a distance of 90 inches, so plus 90 inches for the y, the j hat component. And finally, for the z-axis, it looks like we have 66 inches from the bottom of the board to the wall, but notice the roof comes out a distance of 36 inches. So we'd have to go in, because we're going into the page, we minus on the z-axis, minus k hat, minus 66, the difference of 66 and 36 in the k hat direction. And we know 66 minus 36 is simply 30. So we're going to place that value in for here for the k hat value later on. Now we do need the tension, in order to find the distance, I should say. We do need the distance. In order to find the distance from B to A, we're going to use our distance formula where we take the square root of each of these components, square and add together. So we're going to have negative 5 squared plus 90 squared plus this, the sum of this difference in here is 30, so plus 30 squared, and it is negative. It won't make a difference as far as the answer because we're squaring it. We'll include the negative sign in parentheses here. And now we can determine what the distance from B to A is. So we'd have in parentheses let's see, let's adjust this real quickly right here. So we'd have in parentheses negative 5 squared plus 90 squared plus in parentheses negative 30 squared. We'll take the square root of this number. Oops, apologize. We'll take the square root of this number and we get a distance of 95 inches. So now we can find our force vector, b to a. We already had the scalar component. We're going to find the vector component, what's the direction included. So now we can say, right here, force b to a as a vector is equal to the scalar value we know of 57 pounds divided by the distance we know from b to a, and all this is multiplied by the position vector r from b to a. So if we were to substitute numbers in, we'd have 57 pounds of force divided by our 95 inches. We don't need to include the units for distance and position because they'll cancel out when divide. So we'd have value of -5 I hat plus 90 j hat plus, remember this difference is a total of 30, -30 in the k hat direction. Good. So if we write this out again one more time, we'd have force from b to a is equal to 57 divided by 90. Let's go and compute that first. That would be 0.63 repeating. I'm going to do a little trick here and store this as x. And just multiply that x number times each one of these values. So we have -5 times x gives us -3.11. Oh, you know what? I apologize. It's not divided by 90. It's actually divided by, I wrote 95. It's actually divided by 95, not 90. So I wrote it correctly. So a little mistake here. So always remember to double check your calculations as you go. We have 57 divided by 95. Now I multiply 0.6, so 0.6 times 5. And it's negative, so it's -3 in the I hat direction. Good. Now we have 0.6 times 90. It's positive. So we positive 54 in the j hat direction. And finally we have -30 times 0.6. So it would be -18 in the k hat direction. Good. So now we have our force b to a. We have our position vector r from c to a. On the diagram, notice we have force acting on the board, position vector going from the origin at c to point A. We can now do the cross product by working out our determinable matrix. So we have moment c about c is equal to this cross product, which we know we can also write as the determinant of a 3x3 matrix, the I hat component, j hat component, and k hat component. For our position vector, we have 48, -6, and 36. For our force vector, we have -3, 54, and -18. Now we're going to rewrite the first two columns of this matrix, the I hat and j hat. We have 48, -6, -3, and 54. Now to solve this, I'm going to add diagonals I multiply together going down to the right, and subtract diagonals going up and to the right. So going down to the right, my first one, I have -18 times -6 in the I hat direction. This will be equal to positive 108 in the I hat direction. We have 36 times -3 for our next diagonal. That's in the j hat direction. We have -108 in the j hat direction. Okay, for our next diagonal, we have a k hat, 48 times 54. We have positive 2592. K hat. Now these were all being added, so we could have put parentheses around this as a plus. This will be more useful when we get to the next section where we start subtracting. So now we're going to subtract. So now we're going to subtract these. So we have -6 and -3, positive 18. We're subtracting that positive 18 k hat. We're subtracting this value, 54 times 36. which is 1944. We're subtracting this value, so minus 1944 in the I hat direction. And then we're subtracting this next value. We have negative 18 times negative 48. We'll put in parentheses. Negative 18 times 48. It is negative 864. And that's in the J hat direction. So this will actually become a positive when we end up subtracting a negative. We know it will become a positive. So we'll go ahead and change those signs right now. Now we simply need to combine like terms. We have 108 minus 1944 I hat. So we'd have 108 minus 1944 in the I hat direction, which is negative, we're going to write our final answer out right here, which is negative 1836 in the I hat direction. In the J hat, we have negative 108 and positive 864. So 864 minus 108, which would be plus 756 in the J hat direction. And finally, in the K hat, we have negative 18 and positive 2592. So we have 2592 minus 18, which gives us a value of positive 2574 K hat. And now remember, this is moments. Our units were pounds, force, inches, so we have this moment as pound of force inches, or inch pounds. So here's our final answer for number 24 from chapter 3. And we'll include this vector in our free body diagram as well.
Alright guys, thanks for joining me in another simple STEM solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.